So let me remind you just once again of the central player, the Grotnik ring. So at this point, maybe you're very used to it. Simple ring generated by varieties, simple to define at least. You know how to add, you know how to multiply. That's all there is to the definition. And then the motivic zeta function is the generating function of the symmetric powers. Okay, so what I'd like to do today is to begin. Spend about half my time talking about more conjectures and how they are sort of demolished by geometric / arithmetic ideas that are somehow the same. So let me begin with one early question. So we'd earlier asked the question of is L a zero divisor? And we know why we cared, because that was all about whether R actually, the Grotnik ring, injected into its localization. But there's an even prior question, which is R an integral domain? And I just want to mention, well, it was known well before, well, in this area, well before means still this millennium, but it was known well before that it's not. And there are two different examples, one by János Kollár and one by Björn Poonen. And so Kollár is sort of on the more geometric side, Poonen on the more arithmetic side. But the examples they gave, Poonen gave the geometric example, and Kollár gave the one over the non-algebraically closed field. So I'd like to say the idea in Poonen's example, which is just really simple, which is, so he is going to work over the complex numbers. So I'll put the arrow back to this side, and it's not too hard to come up with two non-isomorphic abelian varieties. Well, that's very easy, but such that furthermore, if they're A and B, such that A cross A is B cross B. And you should believe this is not hard because it's kind of a latticey kind of question. So you could imagine with a little bit of cleverness you can do that. But this means that in the Grotnik ring, we know that A squared is B squared. So that means that we can take the difference of squares. And now this here we know is not zero, because these are complex projective varieties, and we already know that in the Grotnik ring, knowing the class of a variety in the Grotnik ring of a smooth projective variety, the number of components is an invariant. But zero is the class of the empty set. That's got no components. That's got two. So we win. But we don't win so easily here, and so the idea here. So what's left to show, we have two things multiplying to zero, that we need to show that A is different than B in this ring. And we need some sort of invariant for this. And so to do this, we need since we don't know the ring, we're looking for some nice motivic measure, some nice Euler characteristic kind of thing. And so what he uses is the variant of stable birational equivalence classes. So to each smooth projective variety, we have an Albanese variety, and maybe this will be aimed. This brief part of the discussion will be maybe if you've never seen this before, which is probably true for most, just take whatever you can from it. But there is some Albanese variety, which is, I think of it as being like the Jacobian. It's dual to the Jacobian, where that's the Albanese of X. And this Albanese variety, this construction plays well with product. So the Albanese of the product is the product of the Albaneses. And even better, it depends only on the stable birational type. So it depends only on the stable birational type. So that's great, because that means we now have a map from the ring to maybe the monoid, the semi-ring, generated of abelian varieties. And it factors through. Why do we have a map? Well, because we can just go through this map, and we know what that map is, and we know what that map is. And maybe if you want to be a little bit safer and more careful, another way to do this is the following thing, which is we have a map as sets from R to here, and you just need to show that it plays well with Bittner's relation. And Bittner's relation, it's fairly easy to check, since on both sides of Bittner's relation there are two birational things have the same Albanese, and project a bundle over something, has the same Albanese as that original something. So it's a really cheap proof once you have the very clever idea. Okay, so that's one example of a conjecture that we know not to be true. So let me give one more, and this is, again, as usual, I'm not sure anyone, some people would say it was a conjecture, some people would say it was a question, other people would say it's a speculation, and so it's based on the following fact, that in all the examples we've considered, that if we have two varieties, honest varieties, and x equals, let me put it this way. Well, what is clearly true is that if you can cut x into locally closed pieces and rearrange the pieces to get y, then x equals y. So x equals y if x and y are, I guess we can call it piecewise isomorphic. That implies clearly, because you just break it into pieces, use the addition, but it's not clear that the other direction is true. And this is sometimes called something like the piecewise isomorphism conjecture or equidecomposability conjecture. And maybe just as an example, we know that you can blow up P2 at a point, and you can take P1 cross P1. And the only reason we really know they're the same in the Grothendieck ring is because we know how to cut up the pieces and rearrange the pieces. So somehow the statement is, can we get equality in any other way? Or do we ever need minus signs? And just to be clear how this might happen, you could imagine that there's some really big space X. Maybe I shouldn't have called it X, say W. And then you've got two things inside it which are isomorphic, say two isomorphic closed subsets. So these two are isomorphic, but their complements for some reason are not. And are not even perhaps are not cut and pastable to each other. So maybe I should put it the other way around. Two big open sets and their complements might behave differently. So it would be kind of weird if this could happen, but it's a very hard thing to get a hold of. And I think the first result, which I think to say anything about this is hard. And the first really serious thing that was said was the theorem of Qing Liu and Julien Sebag. Which is if K is algebraically closed, if caret 0, so like that, then that's a good shorthand for it, Q bar or C. Then and X and Y are varieties, then X equals Y if one of the following holds. Not only if one of the following holds. One is that in the case of curves, that's true, that's fairly cheap. The second one is the case of a smooth projective surface, or smooth proper surface, they're the same. And now the interesting one, well, this one is already hard, but the next one is when X contains, I guess this kind of subsumes the first one, contains a finite number of rational curves. So some of the geometry of rational curves, and this is going to come up in a second, for some reason, is relevant for a question like this. And maybe back in Putin's example, something which may be relevant is that these, maybe it's back here. In Putin's example, these were abelian varieties. So abelian varieties are special, and so that's also going to be relevant as well. Great. So then, let's see, this is right. I see. Then, thank you. If that's true, and one of these holds, then X can be cut and pasted to Y. Thank you. Right. So in other words, equality, you never need any minuses. You can always just work in the semigroup. Okay, so the reason I like this theorem mainly is because I have no idea. It's a kind of theorem where you have no idea where you'd begin in proving it. Okay, so so now let me talk about demolishing conjectures, more conjectures using geometry. But in the course of it, mention some interesting constructions, which is remember last time we had this ring, which we localized and completed. So that's a limit. I always forget which way arrows go. Okay, I'm not gonna, no arrow, both ways, there we go. This one, This one, when it was just, great. Okay, so so it's this limit, as sort of some limit, some completion of R when you invert L. So I want to say something, an analog which is kind of Bittner dual to this, which is this. Let me define a new ring. I don't quite know what to call it because I don't want to confuse it with this one. But let me just maybe I'll complete it, but there's no L there. I'm going to complete it in a different way. I'm going to define it as a limit, as maybe I'll guess, and there's 50% chance I'm right, that this is that you just take it. It's like an L-adic. These are the L-adic things. And other way? Good. Well, actually, it's backwards on the screen, kind of reversed. So already there's a question of whether you have a map like this, and is it injective, or do you lose information? So let me just put this as a side question, which we don't know the answer to, which is if something is a multiple value of the n for all L, must it be 0? But I want to mention some properties, so one reason we might like this is, unlike the previous example, this plays well with point counting. So if you're over a finite field, you could actually evaluate the point counting map on this, and you're going to get a p-adic number. So somehow that's a very pleasant and good sign that you can. So point counting works, although you no longer get integers, you get p-adics. Another thing is that because we remember that L is in the kernel of this map to knowing what the stable birational classes are, that means that there's a map from R hat to stable birational classes, because we can just mod out by L. So that information, the stable birational class, is also kept inside here. And then the last thing I'll say is that if you take this ring, oh no, this was bad notation, and then you invert L, then you have a map to the completion of R inverted by L. So I guess now my brackets have to be very carefully drawn here, and this is a surjection. This is and maybe the key thing is that if L is not a zero divisor, so in this great world, it would even be an isomorphism of topological rings. Okay, so now let me begin with the fact in geometry, which is going to be useful. This is a theorem of Daniel Litz from a couple of years ago, which is, suppose we have a smooth irreducible surface. And it has its canonical bundle has a section. Then for any M, sim M of x is not stably birational to sim n of x once you go far enough out. And for the different m's, you have to go farther and farther. So just to make this kind of clearer, what this means is that every stable birational class can only appear finitely often. So you're going to get infinitely many stable birational classes turning up. And this is, I should say, you should think it's surprising when you compare it to the examples you might immediately think of. In the case of anything rational, all the symmetric powers are rational. So that's blatantly false here. In the case of curves, once you get high enough, the sim M is a projective bundle over the Jacobian. So they become all stably rational to that abelian variety. So somehow in the other extreme, somehow what matters in this is the fact that you're in the other side of the Fano versus general type line. So somehow that kind of geometry matters. And I also want to mention that the proof uses the geometry of rational curves. It's nowhere present in this statement, but the proof actually uses the geometry of rational curves on X. Okay, so I should say this is some alarming implications for the Grothendieck ring. I should also say this has nothing to do with the Grothendieck ring. This is just a complex geometry. But here's some implications, also due to lit, which is so first of all, you could ask about the stabilization of symmetric powers, and now you can take the limit instead in, my arrows are going there. That the limit of symmetric powers does not exist in this other completion, in this completion. Why? Because if it existed, if you had this limit, then L-adically, the constant term, if you mod out by L, you could pick off the stable birational class, and that never stabilizes. So even like the constant term L-adically, sorry, I guess now L is now a different L than in other talks. It's like a Blackboard bold L. Except when you specialize, it becomes lowercase and italicized. So stabilization doesn't happen here, and especially since one of the properties was that they become isomorphic to this. What this means is that if... Do you need to divide by powers of L? No, that's it. They get bigger. It's bigger in the other direction. So it's a... yes, exactly. It's sort of Bittner dual too. Yeah. So if you take sim nx mod L, then you're going to get stable. You'll be able to remember it's stable birational type. So, but that means that if L is not a zero divisor, then R hat localized at L is equal to RL, and that means that the conjecture of stabilization of symmetric powers, so this Dole-Thomish kind of thing, is false. So maybe I should say it differently, which is these two conjectures cannot live at the same time. They contradict each other. The L not a zero divisor and stabilization. So this is, depending on which way you bet, it's unclear who you think should win, but all the conjectures seem to contradict each other. And so here's another one, which is another corollary. Motivation, okay, this is the motivic stabilization of symmetric powers, and I'll say what I mean, by which I mean you take sim n of x, you take, if x is smooth projective, this is the Bittner dual to turn homology into cohomology. The question is, does this stabilize in this completion? Or so think of it as like R1 over L. Whoops. And that real, not Blackboard bold. Is that visible? Not barely. Okay, so, and this is the thing that was sort of predicted by, depending on how you think about it, Dole-Tom or the Weil conjectures or things like that. Okay, so here's another here's another contradiction, which is that the piecewise isomorphism conjecture contradicts this conjecture over here. And why is that? And how do we use Litt's result for that? Well, if this piecewise isomorphism conjecture holds, if x and y are the same, if and only if you can cut and paste them, well, what that means is that x divided by some power of L could equal y over some power of L, if and only if they had big birational. Let me clear denominators, but the only way this could be true is if x and y had big open sets that were stably birational, but the sim ends, again by Litt's result, the sim ends don't stabilize. So there's no way that that this could stabilize. So thanks to this, we can sort of automatically we get these contradictions between various conjectures. And now a recent preprint, which is the last on this topic that I want to mention, but a recent preprint by Borisov. There are two Borisov twin brothers, so I think it's important to distinguish them, which is just, it's in the notes, but 1412, 6194, it's really, the preprint it's really stunning and really beautiful, I think. So the theorem is that that L is a zero divisor, so that one's wrong. And also piecewise polynomiality is wrong. A piecewise isomorphism is wrong. And great, so he kills two with one example in the same way that this somehow, Litt's result also somehow shows that both simultaneously contradict this. And how does he do it? Well, the construction is elegant and classical, and the proof is elegant and modern. It's a 6-page paper. It's really readable. So the counterexample involves the difference of two Calabi-Yau threefolds, x and y. So again, think of this as kind of think of this as being a Calabi-Yau think of this as being analogous. This is the three-dimensional version of a K3 surface. Think of this as somehow, I think it can't be a coincidence that we get a difference of two Calabi-Yaus here and a difference of 2 billion varieties in Poonin's example. And he shows, well, that this time something doesn't really matter, but something with a big power of L is 0. And then from that, so he shows both that, but then he's also able to show that these things are not stably birational. And I should say but where did this idea come from? It came from his thoughts on mirror symmetry and something called the Pfaffian. You don't need to know about mirror symmetry to understand this correspondence, but the Pfaffian-Grassmannian double mirror correspondence. So really out of very different parts of mathematics, ideas come on how to control this ring. And I should say his argument is over the complex numbers, or is over characteristic 0. And maybe a question is there a counterexample? I mean, we don't know counterexamples. Positive characteristic remains mysterious because a lot of these examples, essentially all, seem to require characteristic 0. So, and it's unclear exactly why. So even assuming resolution of singularities, granting that it's true, which it may be, but may not be, and it may be proved, it may never be proved, we don't know how to use that to get our, to try to kill these conjectures. For number fields, L is, yes, L is a zero divisor. No, well, it follows from the method of proof, I think, not from what I stated. So, and when I say that, I should be a little bit cautious because now I'm saying something off the cuff in the middle of a talk. But yeah, and it is being recorded. But I think the method of proof is okay. Andrew?
Is it clear how this implies piecewise is wrong?
No, he has to. So in fact, in his original version of the paper, he just killed one of the conjectures, and he wasn't really aware of the other. And as a result, he killed various programs of trying to show. So there's a great paper that shows that if L is not a zero divisor, then this is something which I think some people in this room will be familiar with because it comes from an arithmetic source. That a cubic. Let me make sure I say this right. So a cubic fourfold, there's this big, wonderful question of which ones are rational? Are all rational? We know countably many families are rational. And he proved, at least assuming that L is not a zero divisor, that if that's true, then in the middle cohomology, there's something which looks like it comes from a K3 surface, that it really does come from a K3 surface. And this looked really promising because it would give us a real way to tackle this rationality question. But unfortunately, L is a zero divisor, so we're screwed. Yep. That's a good question. I don't think we know whether R is reduced. I don't think I can name something whose square is 0 that I know it's not 0. That's another question that would be great to somehow, whatever the construction is. The great thing with these questions is the answers are guaranteed to be beautiful. The only thing that's frustrating is when we don't have an answer. Other questions or comments on that? Okay, so okay, great. So in essence, in this ring, there are a few counterexamples still standing, or questions still standing. But and depending on who you ask, different people believe different ones. I continue to disbelieve them all. But somehow, I'm very happy that we have these conjectures because then you get things like this, which you can use in other ways. I should say one of the groups, well, maybe two of the groups in my working group are working on things analogous to this. One is which would be perhaps try to use this to do something in positive characteristic because the construction is very characteristic independent. And the other is to look for a big brother of this example, which actually, surprisingly to me, relates to something I'll talk about later today or tomorrow. Okay, so now let me return to these questions of stabilization. In the growth-unique ring. And maybe, again, I want questions, the kind of question I want to mention are that you should somehow expect when you have a family of problems, things should become, in some cases, the answer to each problem might be hard, but if in a family, in the limit, they become nice. And maybe a first example is the point of this, the Dole-Tom theorem, and the hope of this here is that symmetric powers are pretty good, but as they go to infinity, they become better and better and better, and the limit is beautiful, except we don't know the limit exists in this case, except we do sometimes. So let me ask, I want to ask analogous questions, and so let me set this up by asking about something really basic, which is points on a line. And what do I mean by points on a line? Well, my line is going to be just A1. And so the space, these are going to be unordered points. So the space of unordered points on A1 is going to be just polynomials, because of course that has precisely the data of the unordered set, is not the right word, whatever you call it, of roots. And so this is AN. So we're basically showing that sim n of A1 is AN. It's not exactly a proof, but it's a reasonable demonstration. So we got the space of all polynomials, of degree n monic polynomials. And I'd like to ask questions about just discriminant loci in here. So maybe the first approximation, the polynomials that have a double root. But maybe more generally, I'll ask about loci where if you pick any root pattern, so any partition of n into a bunch of pieces, you can ask for the locus of where this root pattern turns up. So for example, if I want those that have distinct roots, I pick the root pattern 1, 1, 1, 1, 1, 1, 1, and have n ones. Okay, so maybe the motivating example will be when you have an m-fold root, and maybe let me just close. Sometimes I'll close things up. So I'll take the closure, and let me now ask you a question, which is really a basic question, which will be our jumping off point. Which is how many, I love this question because it's the first case of something important, but everyone disagrees on what the important thing is because it's the first case of so many things, which is, let me ask about the probability of having an m-fold root. I give you a polynomial, and a monopolynomial, what are the odds it has an m-fold root? So what do I mean by that? And of course this means or worse. That's the only possible meaning of that question. And let me answer this question, tell you the answer in different parts of mathematics, and then once again this link between various subjects will become clear. So let me start in number theory. So in arithmetic, if the field is FQ, well then the question I should say just makes immediate sense because there are finitely many polynomials of degree n that are monic. How many of them have an m-fold root? I should say geometrically. I mean, you want an m-fold root in FQ bar. And here's so this is, I'll tell you the answer, but this is a great exercise, a tricky one, which is, so I want to say the number, we want the number of points in the closure of the set divided by q to the m, and it turns out to be 1 over q, as long as n is bigger than or equal to m, of course, because otherwise it'll be 0. So as soon as, so always, that's independent of n. It's all, the odds is exact, oh, that's even wrong, m minus 1. So it's always this. And so it's a good and interesting exercise to prove it. I should say I'd proposed putting it on our qualifying exams, which are coming up in a couple of weeks, and Brian Conrad said this was combinatorics, not number theory, and should be removed. So it's not so if you're from Stanford and going to take your quals, this will not help you. But I should say try to solve it. Maybe even the case m equals 2. That's already the interesting case to do. And I should say that it's not too hard to solve, but depending on how you solve it, it'll indicate whether you are a number theorist or a geometer. In the sense that the number theorist will get a quick answer by looking locally at every point, whereas a geometer will look globally and try to do things sort of with honest open sets. Okay, so that was an interesting exercise, but now I want to do it elsewhere. So let me do it now in topology. And now there obviously are going to be infinitely many polynomials with an m-fold root. So let me, or maybe let me say not having n-fold root. And let me put that there instead. And so let me ask the analogous question. So what do I mean? What can the question mean? Well, you've got all polynomials, and we want to remove the ones with no n-fold root. That's a big, open, smooth thing. And really, the analogous thing is its shape, its topology, its cohomology groups. So here's a theorem of Arnold. Maybe I should emphasize that this we could have known, and people probably knew 150 years ago. This is not a hard statement. But here's a theorem of Arnold with a little bit more in the easy stuff to generalize the case I'm going to talk about, which is that the cohomology of this group, of this space, is 1 if I equals 0. That's kind of an easy, that's the easy thing. But also when I is 2m minus 1, and it's 0 otherwise. It has two non-zero cohomology groups. And I guess the thing I want to emphasize is that these two ones are exactly that and that, which is what I want to say is that we, on the algebraic side of things, we should have told Arnold what the theorem was before he proved it. And this was around 1969, but that's not how it happened. Okay, and then finally, in algebraic geometry, so this is a topological story, in algebraic geometry, you can cut and paste this locus, and rearrange the pieces and get just an affine space of n minus 1. And then the result follows. So in particular, this case implies that, but it's a different way by cutting and pasting rather than looking pointwise, and has different advantages. And again, this is akin to the different ways I was proposing of attacking the Weil conjectures, where the actual proof, or Dwork's first proof went this way, and we don't yet really have an actual proof. Well, the actual proof goes in a far better, deeper way, but you might dream of this working out. Okay, so now I want to generalize. Oh, first I want to say that where's the stabilization in this picture? So here it's a little bit boring because I now want to let n go to infinity and find out what the odds are. And kind of stupidly, that tends to a limit because there's no n in it. But here there's something non-stupid happens. Again, the answer is the same, but there's something better than just having the same cohomology groups. Each one, there's a natural way of fitting each one into the next one, where you have maybe add the extra root way off near infinity. And the better theorem, the true theorem, is that once again you have these maps of each one into the next one, very much like the symmetric powers. And then as you get farther and farther in, it becomes a homotopic equivalence to higher and higher degrees. And so the stabilization is really a homotopic, is really something kind of strong. And this stabilizes maybe for also slightly more interesting reasons. But let me now generalize this to more complicated discriminants. So now if you ask about questions like, so different ones of these have different advantages, different methods, different fields, but in the case of, let's look at the case where you have an A-fold root and a B-fold root. And so in this case, it's much more complicated, and I'll tell you the answer. What are the odds of having something like this? Well, it's 1 over, let me do the FQ version, the number theoretic version. It's 1 over Q to the A plus B minus 2. That's the odds that a polynomial will have this root pattern or worse. But no counting argument, no point-by-point argument works because it involves interesting things happening at two different points. So the only way we know how to prove this is by the algebraic geometry cut and pasting. And even there, it's not so obvious. And topologically, also the methods used here do not apply at all because, once again, the problem is it's a non-local problem. But at least that means that just as we should have told Arnold what to prove here, what was true, we can at least predict what should be true here. And so there's an implicit prediction that there should be two non-zero cohomology groups, and some topologist will undoubtedly be able to prove it at some point. Okay, great. So, and then I should say, when you pick weirder and weirder root patterns, then in this case, it clearly stabilizes, there's no n, but I should say as things get weirder, so if you have 2, 2, 3, and then 1, if you have something slightly more complicated, then it's not constant. It goes to some limit. There's some power series in 1 over q. So this is a too simple example. And once again, it tells you how to count things arithmetically. It also predicts something topologically, such as the fact that you'll have infinitely many non-zero cohomology groups. Actually, that even implies that. And so that's the story I want to generalize. I want to count points or look at the topology of things or understand the algebraic geometry of things, of configuration spaces on varieties. And I think of the case of AM or of AN to be the topologically boring case. It's flat, there's no shape involved. And now I want to toss in, do this for an arbitrary variety. And so now I want to do this for a general X. So I want to have these sets and also their closures. And so these are open subsets. So this is, what does this mean? That's a partition. I want a bunch of points on X whose multiplicities who come together in clumps given exactly by that partition. Like 2, 1, 1, 1, 1, 1, 1, 1 means 2 of the points are together. And this is going to be the closure, which means 2 points together or worse. So let me make a table, maybe to do things somewhat historically, which is in topology. So in topology, again, even this is rather recent too. So this is going to be a stabilization result where I'm not going to tell you about the cohomology groups of this space, but I will tell you about it as the number of points goes to infinity, as I add a lot more ones to this. So you should think of this as kind of the odds, the topological odds, or this will soon be an actual number. And the odds of, if you take n points, what are the odds of 2 of them being on top of each other, n unordered points? What are the odds of 2 of them being on top of each other, and where n goes to infinity? That probability tends to something nice. That's going to be the upshot. And the first really successful work in this area was Tom Church's Inventiones paper, which appeared maybe a year or two, very recent, a year or two ago, where he answered this question. He somehow gave in terms of the topology of X, and again, you should think about this very much in terms of symmetric powers, in terms of topology of X and some representation theory. He gave an effective algorithm for theoretically effective algorithm, whatever that means, in the sense that I couldn't program it successfully, to actually work out all the cohomology groups of the space. And then Randall, I should mention Randall-Williams, Oscar Randall-Williams also has a proof in this case. And this is a nice open set and smooth. But this is not. It's singular, enclosed. And so in some sense, topologically, this was the obvious space to look at. You had a nice answer, and this seemed like, well, of course, this is the wrong space to look at. But in algebraic geometry, I should say that I'm going to have some hypotheses here. I'm going to assume that M satisfies this conjecture, the stabilization of symmetric powers conjecture. But okay, we know it's true for rational and stably rational varieties. But I should say, if you care about Hodge structures or point counting, it's still going to be okay. So this will be true for all X if you just care about things, concrete things like that. I should say that everything I say that involves things I've thought about, it's joint with Melanie Wood. So in this case, it turns out that the limits exist. And that's kind of cheap. I mean, that hardly, but maybe much more interesting is that you can say what the limits are, and the answers are in terms of motivic zeta functions. So the answer you write are writable in terms of motivic zeta values. So in both cases, it's motivic zeta values. And the interesting thing is that these are the nice ones. These ones are hideous. Well, I wouldn't say hideous, but these ones you get very short, beautiful formulae that have really nice descriptions, and from that, of course, you can deduce these, but it's kind of ugly. And in fact, things are awkward enough that it's impossible to check whether these agree. I mean, they must, because presumably they're, they should. They don't. I wouldn't say must. You should want to match them up, but these are open, and you can't quite. It's an imperfect. The topological world is imperfectly mirrored, and that suggests that really the right thing to do, that these are the right spaces, not these, even though they're singular. And then there have been a sequence of because sort of motivated from our side of mathematics, interesting, a really nice paper of Coopers, Miller, and Tran, and they're all three topologists, proved various versions of this that were predicted, but in the course of doing it, they proved much better. The results are better with z coefficients, for example, and they're optimal, and they're sort of provably optimal And so this sort of led, in a way that sort of, the way mathematics happens is by this back and forth between various fields. And arithmetically, I should say that then this implies things here and here, and I don't think there's any way to currently prove these directly. We don't know how to point count directly without going through, without thinking this way, because the questions are not local, so non-local theories will be helpful. Okay, so let me just give an example of a kind of formula, which is, let me say you have n points on x, and I want to let n go to infinity in a minute, and I want to say, what are the odds? Let's count points. What are the odds that there are exactly m multiple points? So like for example is, so maybe one example is polynomials. What are the odds that you have a polynomial with exactly m multiple roots, but now I want to mix in the topology of x as well. I want x to be interesting too, and the limit turns out to be something over a motivic zeta value. It's this motivic zeta value. You plug in, so you think of this as zeta of minus, or zeta of 2D or minus 2D, I forget the convention. And if you want V zeta function, if you want a point count, you should put the V zeta function here. And I'll tell you what the numerator is. Let me just remind you what this is this is 1 plus, well, the general term is sim n of x, and then you plug in 1 over L to the 2D to the n. Okay, so it's just a generating function of these things. The numerator is a generating function too, and of course, and it is, I'll just tell you one term, and the numerator is, well, it's inside here. Let me call this sim, temporarily, I'll put 1 over L to the 2D to the n, but that doesn't matter. This is how you want n split into exactly m parts. What's that? There? That's a 2D, yeah. This is meant to be exactly that. And you can't read that either, so I guess that doesn't really help. but it's that there. So I guess the thing I want to say is it's not so much the value, but it's what goes here. So this is n points in general, floating around. This is, I want the n points to be in exactly m clumps. So I want them to be sort of m points with multiplicity. And maybe this sounds like a weird thing, but I'm going to say 3 things, 2 right now, and 1 because of a coincidence very soon. So very soon, or maybe next, not so soon, tomorrow, which will make this a bit reasonable. So the first thing I should say is that if you take m equals 0, there's no way to split n into 0 parts unless n is 0. So we get 1 over zeta value. If m is 1, you can get something simple. Maybe I'll skip it. But for each m, you can really write this in terms of I mean, I'm writing it this way deliberately, but you can really write it in terms of zeta values in a not too hard way. And maybe let me conclude by telling you, so next time I want to do kind of the dual statement, which somehow ends up being, there's less you can say, but it's more fun even. But so for example, the affine, so here are maybe a few comments on a result like this. First is that when x has no topology, you recover the things about polynomials that I described before. And secondly, on a general x, the odds of n points being distinct, or of infinite number of points being distinct, is 1 over zeta of twice the dimension, which can be shown otherwise. And so it also leads to explicit conjectures in topology and also arithmetic geometry of things which must be true that we do not know how to prove. And I think I can give examples, but I think I probably won't. And maybe the very last thing I'll say is that the fact that you have, in the topological analog, when we see zeta functions in number theory or algebraic geometry, we like these gadgets. These make us very happy. And they somehow translate into something on the algebraic side, on the topological side, which means there should be some vague, this is a very vague pipe dream. When you see zeta functions on our side, you should be telling the topologist, you should be looking for a sphere, a zeta value of m is a sphere bundle with, where the sphere is 2m dimensional or something like that. So there should be some really even better link between our side of the fence and their side of the fence. Okay, so next day I will tell you about hypersurfaces and then get into some Bargavology, hopefully. Thanks.